Okay, good evening. So let's finish lecture 6. And I'm going to redo some of the slides so that we have the context in mind. It's been 2 weeks since we interrupted this lecture, so I don't want to assume that you still remember what was there. So we're going to start from compilation of function application, right? You remember the syntax, right? It's expression applied to expression 1 up to expression n. E is assumed to evaluate to a function of n arguments, or possibly less, right? We have this concept of partially applied function, or actually possibly more. It doesn't have to be exactly n arguments. So the important thing to remember here is that we're compiling the arguments in reverse order. All right? And why is that important? It's important because as we go through the program, we're going to evaluate S1, so when I say evaluate S1, actually we're executing S1, right? Sn, right? We start with Sn. Sn will go into the stack, right? And then Sn minus 1 will go into the stack. And when I reach the point of S, what I see in the stack in order are S1, S2 up to Sn. If I were to pop from the stack at that point, I'm going to pop in the order S1, S2, Sn, right? So the arguments are going to come in the natural order from the stack. And that's the reason we want to compile in reverse order. That's obviously a bit of a strain on the compiler. So if you're writing the compiler, right, you're going to have the abstract syntax tree and the node representing the application in the abstract syntax tree, right? So this is the node representing the application, right? And it's going to have children. One child is going to be E, or the subtree corresponding to E. Another one is E1 up to En. So in thinking of the traversal of the abstract syntax tree, here you're going to have to go through from the right child up and in sequence up to the first child, which is in fact the function. All right? And then the instruction for executing the call is call, C-A-L-L, which you see there. And we need an argument to this instruction, right? At the level of the virtual machine, this instruction has an argument, which is the number of arguments to the function that were passed in. This is important to keep track of whether the function is over-applied, under-applied, or exactly applied, and it's going to come out later. We're going to see that from the compilation of the function of E, we also have the number of arguments that the function is capable of taking. And the interplay between that number, which we typically call m, and the number n, right, is going to decide how we execute the return. All right. So going back to the function definition, all right, so let's remember how do we compile a function definition. We're going to introduce actually two new instructions here. One is LDFS, and the other one is return. LDFS is the function that pushes the value of a function into the stack. All right. So we're going to have to decide later to show later what is the value of a function. And actually, if you remember, because we went through this already, it's a triple. Right? It's a triple containing an address, an environment, and a number of formal arguments, a sequence of formal arguments, right? So LDFS creates that triple, and it's putting it on the stack. But at this point, we're not concerned with what LDFS is doing, but pretty much we're interested in how to compile a function definition. So assuming that E translates into S, right? So E translates into S. Again, we have to be compositional, right? We have a function definition here where E is inside, right? And we have to take advantage of the fact that we have already compiled E, right? And it's the compilation of E is here in S, and we have to put some structure around it to create the function definition, right? So the symbol is going to be LDFS that tells us that we are going to load a function into the stack. That function is translated into a number of instructions, and the start of that function is right here. So if my PC is here, right, the start is right here. And if you remember, we were playing with that PC plus 2, right? At the point when we are going to define this, we're going to essentially, part of that triple is going to be the address of S. So what are we saying? Load a function symbol, right, which has a bunch of free variables and a number of arguments. All right, into the stack. And the address of that function is known. It's the current PC plus 2. So we pretty much have all the elements to compile that function. Okay? Now, why do I need VS? X1 and Xn is pretty clear why I need it, right? They're arguments to the function. So at some point, those arguments have to get values. And when do they get values? Not now at the definition, but rather at the time of the call, right? So X1 are the formal arguments to the function, right? X1 up to Xn are the formal arguments to the function. They don't get values now. So we have to put them there so that we would know to what do we need to assign values at the time of the call, right? So that's a natural thing. It's normal to expect to put those there. The less obvious thing is, why do we need the VS, which are variables that are still free, that are still unbound? And I was telling you, what are those variables that are unbound? Well, if I have a function fun that defines x into x plus y, this y is a free variable. Doesn't get a binding inside a function. It appears undefined at the time of us focusing on this part, this fragment of the code, right? It might be defined in a larger scope, but at this point we're just focusing on this fragment of the code. That's what the compiler is doing right now, and it doesn't have a definition for y. So what can it do with that y? Since it doesn't know where it is defined, it can just keep track of it, right? That's the only thing that it can do. It can say, oh, I encountered this y which was unbound. Let me see if I can bind it later. All right? Is that clear? That's the only thing you can do, right? So as the scope enlarges, at some point there will be a definition for this y. Y is maybe the argument to a larger, more encompassing function. And at that point we're going to say, oh yes, well, y gets its value from here. Okay? So this is the reason why we keep track of these variable VS that are not bound. We say that they appear free. Clear? All right. So what's the difference between these? Oh, okay, so the other one is with symbolic variables, right? So let's look a little bit more at the structure of this translation. So we are saying that we're going to load a function into the stack, right? And we have the VS and the x1 up to xm, and then this function must have an address, right? And this address is currently implicit. We are relying on the fact that the compiler will always translate in this way. This is a bit fragile, but it works for the time being, right? That immediately after LDFS, the compiler is going to put a goto. Goto takes one slot, right? And the beginning of the function is at PC plus 2, right? So the address where we have to go is implicit at the time of processing this thing, right? Then, once we have created a triple, so we have 1, 2, and the address is the third part that goes into the stack, we are defining a function. The function is laid out here, all right? But we're not executing it right now. We're just defining it. So that code must be skipped. Therefore, immediately after LDFS, we have a goto that skips to the point, skips right here, right after return. Okay? So, how many instructions are from here to here? The length of s plus 1, right, obviously. So we have to jump relative, goto_r is jump relative, the length of s plus 1 locations. Okay? Now, we can do this with symbolic labels. So instead of saying go to and specify the length, we can say go to a label L and say in the code, right, the compiler can say in the code that the label L is right here after the return. So effectively, we define the function and avoid the execution of the code by jumping right after it. We wouldn't be able to execute the code right now because we wouldn't know the values of x1 up to xn. Right? Is this clear? Is it too clear, or I'm definitely not sensing acceptance? So we are either bored or you're lost. One of the two. I don't quite see that you are following and enjoying it. So I mean I would prefer that you stop and ask questions if you think I'm going too fast. You stop me and ask questions. All right, so we have defined this instruction, and we have defined the translation, introduced this instruction, and let's try to understand how it is executed, right? So this would be the semantics of LDFS. What does the virtual machine do when we execute it? So the rule says the following: whenever the current instruction is LDFS, right? Remember that this is the state of the virtual machine, right? S applied to PC is the value of the program counter, and is the storage of the at the index of the program counter. And whenever that is the instruction LDFS with some free variable v1 to vm and some arguments x1 to xn, right? What does the machine do, right? So the machine performs the transition from the current state into the next state. The current state is OS-PCE. Do you remember what these are? So OS is the operand stack. PC is the current program counter, which has to be the same as this one, right? So if we're saying that this is the current instruction, we want the PC here. Otherwise, we wouldn't be providing a definition for LDFS. And E is the current environment, which is an assignment or an association, better said, a mapping from symbol names to values. And what values are we expecting to find there? We're expecting to find values for the symbols v1 up to vn, right? If we don't have those values, we can't execute this. These are values that are defined outside our function. So if the environment doesn't provide those values, we're essentially stuck. right? So we have that expectation that all v1 up to vn are defined inside E. Okay? What is the next state? Well, if you remember, right, we have to create a value for the function, right? So this is my new operand stack. All right? And so this was the old one. This is the new one. What does it look like? Like a new object has been placed in here, right? So previously our objects, our values, operand stack contains values, right? Were what? Integers and booleans. Now we also have functions. And I was telling you that function values are triples. So we have just put a new function in the operand stack, which we represent as a triple, right? We need a start address for that function, which is here, PC plus 2, because we have LDFS followed by go2, followed by the start of the function, remember? So the start of the function on the previous slide is at 2 locations away from the current LDFS. It's at current PC plus 2. So that's going to be the start. Then we need the list of arguments, right, x1 up to xn. For these we don't yet have values. All right, so we have to say, oh, remember these symbols, because you don't have values for them. Whenever they get values, we can execute the function, right? However, for those symbols that are free, we should already have values. If we don't have values for those, we're stuck, right? So we're going to take from the current environment, we're going to take only the mappings for those free variables. I don't want to take the entire environment. I could, but I don't want to be bothered. It's too large. So I'm going to take the projection of that environment with respect to the keys represented by the current free symbols, right? Because the environment is a mapping. So it has keys and values, right? So I'm not going to take the entire environment, but the projection to these symbols. And this triple in the inner brackets, it's getting a bit cluttered, right? So you see the inner brackets here. This triple is the value representing the function, the lambda. That's what it is. We have put it in the operand stack as we did with all the other values. That's where we put the integers, the booleans, and now since lambdas are values, we also put the lambdas there. Is this clear? All right. Then we have executed this instruction, so PC goes to PC plus 1, right? Which now we know it has to be the go-to. So immediately after this, we're going to execute a go-to. And then we keep the current environment unchanged. The current environment was just a source of values for the free variables, but we didn't perform any change on that. We didn't add any new symbols. Cool? Yes?
What does E hash v1 to vn do?
Again?
What does that E hash v1 to vn thing do?
So this is the projection. This is what we call the projection, right? So if I would have an environment, let's say variable A maps to 1 and variable B maps to 2, right? And I want to say hash the set A. Then what I keep from here is just A1, right? It means that I'm not interested in anything else but A. Okay? And it's clear why, because all those other symbols don't appear in the function, so why carry them with me? It would be inefficient. Okay? So it looks a bit strange because the value is so large that you miss the fact that it's actually prepended to the OS, which presumably has a lot more elements than just, right? But this is just the tip. This is just the tip of the stack. All right? OS contains many more values. Right? And what we've done by transitioning from here to here is to just add one more value to the OS. Okay? Yeah.
So if you just, instead of fetching those values and projecting them out and getting their values, if you just store that E1 to VM are still variables, because you're still taking E forward, whenever in the future you require it, you could project it at that time, right?
Actually, no, because they would have changed values, right? So this is something that I showed you last time. So actually, you can in a different semantics, which would be called dynamic scoping, right? So programming languages have, for scoping rules, there are two types of scoping: dynamic scoping and static scoping, right? Most modern languages are statically scoped. There are very few that are still in use. One is Perl, and the other one is Lisp, Common Lisp. These are the only ones that are dynamically scoped. All right, and let me remind you then, we had that discussion last time, right? Where I think I picked Python, and let's do Python 3. Make sure it's Python 3. Right, so let's say I have a variable a equals 3, and then I define a function, and I'm just not going to bother with any variables, and I'm going to say here x equals 10, right? Sorry, a equals 10. And then def g, and then I'm going to say here, the tabbings are a bit strange, non-local a, and then a plus 3, and then I'm going to return g, okay? So now I will say h equals f. All right. So when I call h, what am I going to get? I could get either 13 or 6. Which one am I going to get? When I do this, 13, right? So if we were doing what you suggest, we would be getting 6. Does it make sense? All right, so that's why we are taking that right? So it seems more complicated, and it seems that, I mean, obviously it would be easier to take it at the time of the call, right? And that's why Common Lisp was one of the first languages. Lisp was one of the first languages, right? So at that point, they didn't think through, and it seemed like, take the easier path. It resulted in a very unnatural scoping for languages, right? So dynamic scoping is actually not very useful, really, because it doesn't allow a proper encapsulation. But it's what people have used for some time. Perl is actually by default still statically scoped, but it's very easy to make it dynamically scoped, right? Python can also be dynamically scoped if you know how, right? So you can access any kind of namespaces at any point. And then, for instance, if I would be able from Python, from inside that function, to always access the outer A as opposed to the inner A, right? But I wouldn't just be able to write it as A. I would have to go and traverse all my environments up to the global level, and I would be able to access the A. Right? So because there are situations where dynamic scoping can be useful. Is this clear? Does this make sense? Cool. So this triple is called a closure. It's a standard concept, right? It's not just a lambda, right? Because when you say a lambda, depending on the context, in a lot of languages, the lambda is expected to be pure and independent of the context, right? So a lambda is a pure function whose value depends solely on the variables, right? So here we are a bit more relaxed. The value depends on the input variables, on the arguments, and on the environment, right? So then we have to take in the environment at the time of the definition. Closure. All right. So now, what do we know about function calls from most languages that we've worked with? You call the function so you're in this place in the program. You call the function, it executes, runs, returns a result, comes back to the point from whence it was called, right? You execute a little bit more, call again the same function, and it comes back again from where it was called, right? It sort of remembers from where it was called, and it can go back there, okay? And we have to provide some sort of a mechanism for this to happen, all right? And now you think of the fact that the calls are actually nested. You call a function which calls another function which calls another function, and then the returns are sequenced properly, right? And they come back in exactly the reverse order of the calls, right? And this suggests that the correct storage for these calls should be a louder stack, right? So this is what we call the runtime stack. All right, it's going to remember the place from where the call occurred in the code and be able to return right there. So I was telling you last time, this is what processors see as the stack. You know from computer organization that a CPU has a stack, right? That stack is not the operand stack that we've been talking about. It's actually the runtime stack. The equivalent of the operand stack is the CPU registers. All right? Most of CPUs don't have an operand stack. They have registers. Those registers can be organized as a stack for some CPUs, including the Pentium now. So there are instructions in the more advanced Pentium architectures that can regard the set of registers as a stack and operate on them, right? But the idea of a stack machine is very old as a theoretical concept, and it was implemented in JVM, and it leads to simpler translation. So this is why we're adopting this concept, and we're using the operand stack for our virtual machine. It's not a concept that is very accepted in hardware. So never mind. The new runtime stack contains what we call stack frames, right? And it has the ability to restore the sort of state of the machine at the point of the call, right? What's going to happen since we have placed the environment in the function definition? What do you expect to happen at the call? We're going to alter the environment somehow, right? Because we're going to have to take those definitions that we encapsulated in the function definition, those variable symbol definitions, and we're going to have to alter the environment to allow the function to execute with those definitions available to the code, right? When we come back, what do we want to see, right? So if I go back into the code, which should be here, if I say A, I will see the value 3, right? So somehow, right, at the point of invoking H, at the point of invoking H, right, somehow the environment would see that A is 10. But as we come back from the return to H, we're going to see that A is 3. Right? We only have a single environment. We only have a single placeholder for A. yet the value of A outside H and the value of A inside H are different. How is that possible? Well, because at the time of the call, we're going to take the environment from the function definition and we're going to clobber the current environment with it, which means that whatever definition for A I had, as I go inside H, I'm going to say that A is 10 from this point on. I'm going to execute H, and when I come back, what do I need to do? I need to restore the old environment, right? Which means that at the time of calling H, I must have saved the environment, right? So that's what's going to happen at the time of the call. When we call, we're going to save some stuff. The place from where we call, so we can return, and the environment, right? So we can restore it. We can restore the value of A to 10. And also, we have this situation with how many arguments do we have compared to how many formal arguments versus how many actual arguments do we have, right? We can have over-applied, under-applied, and exactly applied functions, right? So we have to store this relative relationship. So that's something we're going to put there as well. All right? So we're going to have a triple. The frame in the stack frame is a triple. The stack frame, not the frame in the stack frame. The stack frame is a triple. So it's the number of residual arguments, we're going to call them, right? So how many do we still have to apply? The address from where we are called, and actually this is not the address from where we are called, because that would be the call instruction. It's the address immediately after, right? That would be sort of the return address, and the environment that was available at the time of the call and which we would have to restore at the point of returning from the call, right? Does it make sense? Cool. So let's explain the residual argument. So we have over application, and when m is less than n. So when we have a number of formal arguments that is less than the number of actual arguments, right? I'm hoping this is correct. Okay, so, all right. So the instruction says, call, right? So call and use n arguments from the stack. Okay, so now if you think of how the stack was translated, the first thing in the stack is the function itself. And then I have values in the stack, right? So since I don't know how many arguments the function was supposed to take, right? I'm going to look at the place of the call. So there's some place where I would have this E applied to E1, E2, and so on up to En. So at the point of the compiler sees this, at the point of seeing this, it will say, oh, I am passing in n arguments, right? So that's the number. However, when the function was defined, it might have had m arguments. All right? There's no guarantee that the number is the same. We would want it to be the same, we would think, but in general, actually, it's possible that it weren't. We discuss situations where it weren't, right? So this, what we're describing here, works well when m is less than n or m is equal to n. All right? At that point, it works very well. The point when it's greater, we're going to handle that via syntactic sugar. So we're going to take that kind of construct and translate it into something that can only lead to one of these two situations. All right? So we're calling. What do we have to do at the point of calling? So this is an instruction that we haven't introduced. This is the virtual machine instruction this is the current virtual machine instruction, right? And we're again transitioning from the state here. You see the arrow here, right? And this is the final state. So we're going from the current state into the next state. Okay? So what do we have to do? We have to jump to the function, right? We have to go to where the function starts in the code. All right? Our function is at this address, has these arguments, formal arguments, and has this environment that was stored at the time of creating the function. Okay? Then we have at least m values, v1 up to m values that we can use as values for our arguments. Right? They sit in the stack in reverse order, if you remember, right? So this is the rest of the stack. This is the current PC, and we will have to return, not right here, but at the instruction following here. We're going to have to return at PC plus 1. We have the current environment, which is different from E prime, and we have our current runtime stack. So now we know that we have a new element in our state, which is the runtime stack. And what's the next state? Well, all this is removed from the operand stack, right? The essence of evaluation of execution is to remove stuff from the operand stack and replace it by a result, right? We take a lot of stuff from the operand stack, typically at 2 arguments, and put back a result. So the same is going to happen here. We're going to take m plus 1 objects from the stack, and when we return from the function, there's going to be a result. Okay? So this is the current OS, and then, never mind this PC, we are jumping to this address. This is where the function starts, right? And then we're going to augment the current environment with the environment that we created at the time of creating the function, right? So E prime is this environment. Sorry, I misspoke. So we're going to take this environment, which is the environment we have to use, and we're going to augment this environment with values for our formal arguments. So the formal argument x1 takes the actual value v1. The formal argument xm takes the actual value vm, right? So now what do we have here? We have an environment that contains a value for every single symbol in the function definition, right? All the symbols in the function definition could be divided into 2 categories, free and bound, right? So for the free variables, we already had this guy E prime. This guy E prime was already giving me values for those. The only thing that I haven't gotten yet is values for the arguments, for the formal parameters, right? For the formal arguments. And now we are providing those values. They are coming from the stack. Right? So the formal argument x1, which is here, gets the value v1. Where do we put it? How do we create that mapping? Well, in the environment. That's the most natural place to do it, right? So now this environment that we have created right here has values for every symbol that I'm going to see inside the function. Clear? So I can go and execute the function. I can very safely jump to this address and let the machine go. Okay? Now, the last thing that we need to do is save the current state is not the right word here, but save the current configuration so we can return from the function, right? So what do we save? Well, one important thing to save is the environment. It's not written first, but it's probably the more important thing to save, right? This we have to restore. This symbol x1 might already be defined in E, all right, with a different value, because it comes from a different scope, right? It's what we typically refer as a name clash, right? Name clashes are legal in most programming languages, and we have to handle them, right? So While I'm executing the function, that symbol gets a new value, but as I go back, I have to restore the old value. So this environment will be useful at that point. I have to store the return address, which is not PC. The PC is where the call instruction is. I have to go back at the instruction right after the call. And, well, we might not have used all the arguments that were passed here. We're passing n arguments. The function is only able to consume m, which is smaller, right? So we have what we call n minus m residual arguments. If this number is not 0, let's say, so if it's 0, it's all fine. We're going to come back, completely restore the state, and move on and continue execution, right? If it's not 0, what do you think happens? So remember, when we come back, we're going to hit the return address, right? When we come back, we want to have a result at the top of the stack, right? If this number is greater than 0, this result at the top of the stack, what do you expect it to be? Louder.
Another closure.
Another closure, very good. If this number is 0, this return value might be a boolean or an integer, or fine, right? But if this number is greater than 0, necessarily what comes at the top of the stack has to be another closure, right? And you've seen this right here, right? So this is a function which when compiled becomes a closure. The return value is another closure. I'm returning g, right? So now a very interesting situation would be where, so I gave a sort of a simplistic example where we have no results, but I can define f to take an x and define g to take a y, and I'm going to return x plus y, right? And I'm going to return g here, right? So now you see f taking a single argument, right? But I can very well say f applied to 2 and 3, which would be the carried version of f taking 2 arguments, right? And returns 5, right? Why is that possible? Because when I applied it to 2, the result is a function which can further take the argument 3 and returns a result, right? So you can think of this as f has been called with 2 arguments in our language, but it was only able to consume 1. But so when I go and compute the number of arguments, there's one residual argument. This guy returns the g, which further takes the 3 and computes a result, right? So whenever I have this residual argument, which is the number of residual arguments is greater than 0, what I have as a result of this application must be a closure. Clear? Cool. All right, so that closure can consume n minus m arguments and return a result. Or it might consume less than n minus m arguments, in which case I repeat, right? I have some greater than 0 residual arguments. I'm expecting as a result another closure, and I'm going to keep going and going until what I'm getting here is 0, right? But the interesting thing now is that what do I do when I encounter a return? And we're going to see that, right? I have to do different things on whether this number is 0 or not equal to 0, greater than 0. Oops. That was not quite what I wanted to do. Okay, here. So let's see what comes next. All right, so let's see what do we do if we have over-applied functions, right? When m is actually greater than m. So that's an example. Oh, sorry, over-applied are fine. Under-applied functions. So what do we do when we have under-applied functions? Right? The over-applied function, we just saw the example in Python. I think that's fine. This would be an example of an under-applied function, which is also fine, right? So the x becomes 2, and then this is equivalent to fun y goes to 2 plus y, right? Once I have applied it to 2, x takes a value, we still have to apply it to y. So under-applied functions should be syntactically correct. The thing is that they're very easy to handle as a pre-processing step, as syntactic sugar, right? So I can very easily wrap it into another function, right? And this extra argument goes in here, so this becomes a exactly applied function, and problem solved, right? So the problem of under-applied functions, we can consider that it never arises in practice, right? At the point when the compiler comes in, the program has already been transformed so that it doesn't have any under-applied function, so we don't have to handle this case. Is this clear? So we don't worry about it. So let's see, how do we return? Okay, simple case, no residual arguments. All right, there's a value at the top of the stack. So the assumption is that as we execute the body of the function, right, a result is at some point placed in the stack, on the stack, right? So that will be computed, will be considered as the result of the function. And in this case, case, because of this, well, we can think of the function as a user-defined operator. Our general treatment of operators was some arguments go in the stack, then the operator comes, pops them, puts the result, right? So our function does the same. Takes the arguments from the stack, computes the result, puts the result back, right? A function is nothing but a user-defined operator. So the value that is at the top of the stack is the result, and we're fine with it. We can essentially leave it there. We don't we don't need to do anything. It's the result. The result sits in the stack, right? At the top of the stack. But upon encountering the return, all right, we have to restore. We have to go back from where we were called and restore the environment. So let's see what happens. At the point of seeing the return instruction, the stack frame, the runtime stack must have a stack frame at the top, right? It must have, because in order to encounter a return, we must have encountered a call. The call always comes before return, if the compiler is correct, right? So there's a frame at the top of the stack. This frame contains a number of residual arguments, which we assume to be 0, a return address, and a environment of the outer scope. Okay? So what we're going to do is essentially use this information to perform the restoration. So in the next state, the PC has been restored to whatever was saved in the stack frame, and the environment has also been restored, right? By using these records, how do we get these records? By popping them from the runtime stack. So this is the runtime stack after popping the record, all right? But the operand stack stays unchanged. That V was there before the return, computed as the result, and will be there after the return to be seen by the outer environment as the result of calling the function. Okay? Cool. So this is the simple case. And I keep pressing escape to erase the markings. Sorry for this. Now, what happens if we have a number of residual arguments that is non-zero? So in this case, we have to immediately perform another call. The return doesn't go back to the original place of the call, but engages in consuming more arguments from the stack. All right? So one important thing is that at the top of the stack, if this number is not zero, right? At the top of the stack, we must have a closure. Otherwise, we're stuck, right? But if the type checking was correct, this shouldn't happen. We should have a closure. So the closure, as previously, would have an address, would have a number of arguments, would have an environment. Okay? And think of the Python example as I gave it to you, right? We return the inner G. So the inner G has arguments, has an A inside that has to be locked to the value of 10, and that's our return value. That's what would be at the top of the stack as the return from the outer function. So we are inside calling the outer function f, right? And we're returning G. So because we are inside f, we have a stack frame at the top of the runtime stack. And what we're going to do is alter this and reuse this. We can't return to the original place of call. We have to alter this and reuse this in order to consume further arguments from the stack, in order to perform the new call. Okay? So it's like a chained call. It's a call inside call, which is really true because I'm calling f, but it automatically calls g. Right? So what's the next state? Well, it's a new call. So this stuff has to go away from the stack, has to be extracted, right? So this is what is left. The OS is left. We're jumping to this address. Okay? So we're leaving f, we're going inside g. We're altering this environment, we're augmenting it with arguments, right? The formal arguments take actual values that were computed and placed in the stack, right? And what happens to the runtime stack? Well, this is a new function call, right? So it may be the case that we are still not consuming everything, right? So all we can do is say that number of residual values, residual arguments is r minus m, right? R might be equal to m. It was in our example, but it's not a rule, right? It might still be different. And this is still the same as here, right? The return address of the original place of call, which is the main program for our Python example, is still the same. Where we have gone from f inside g, but the place in the original main program is still the same as a place of return. So this doesn't change. The environment that was available in the main program at the point of the call is still the same. That doesn't change either. Okay? So this is it. We have essentially jumped from the end of f to the beginning of g. Right? Which is what needs to happen, right? So if you think in terms of the definition, this is the definition of f And then inside here, there's a definition of G. So when I say that I'm returning G, right, and I have this argument here, from the end of F, I have to go to the beginning of G. Does it make sense? Yep. So this is what it is. It's essentially a chain call. And it's going to be chain call after chain call after chain call until this number becomes 0, at which point the rule on the previous slide applies. Yes? So we're going to look at, now the circle closes, right? And I wanted to make sure that this is understood. So we have a system of things that have to, when combined together, they have to work, right? So the way you translate the function definition, with the way we call functions, with the way we return from functions, right? This is a system that has to, if each instruction does something relying on an assumption that the next one is going to do something else, right? So you only understand how they work if you look at all the three as a whole. All right? And you have to spend a little time to figure that out. So I want to give you half a minute or so to think about all this. And if there are any questions, I'll be happy to answer that. Otherwise, we're going to move on. This is perhaps the most important part of the course, right here. A lot of the behavior of programming languages will become clearer to you if you have understood this. All good? Yeah. So we're going to try to organize the environment, refine a little bit more the environment, right? Because we have a bit of a problem with the fact that we have to remember the names. We don't want to remember the names, all right? And actually, we don't have to remember the names. If we put them in the right order, right? If we put them in the right order, then we can always use numbers, and then we don't have to carry the list of names, like this list of names, this list of names. Oh, come on. This list of names. We don't have to carry that with us, right? So, in order to do that, because we positionally we know that they go from 1 to m, right? In order to do that, however, in the translation, which is happening here, right? Remember that this is translation of identifiers. right? We would, what we used to do was, we had the assumption that we're carrying this in the environment, and we were saying that this is the symbol X, right? Well, I don't want to worry about symbol X anymore. I want to worry about the index at which this symbol would be stored in the environment. All right? So what I have to make sure is that each symbol actually translates into a separate value, right? And it's going to sit in the environment at the index represented by that value. All right? And in this way, I can optimize by not carrying over the symbol names with us in the function definition. Right? I will know that I have 3 arguments, and inside the function code, I'm going to have, instead of the argument x, y, z, I'm going to have the argument 1, 2, 3. All right? So argument 1, or argument 0, 1, 2, argument 0 sits at the 0th position in the environment array, and so on. So that's going to make things easier for the compiler, right? Compilers like to, or code likes to work with arrays, and that's simplifying things. All right. That will also make it easier to copy from the stack to the environments. All right, because if we're organizing the array in this way, we're just extending the array by a few locations, and we're done. If you look at GCC and the way GCC compiles code, at how you perform a function call and see the sequence, this will become very clear. So applications remember the number of arguments. It can be either fully applied or over applied, but never under applied, right? Because we have our preprocessing. So let's look at an exact application example, right? So and in this process, we are going to drop the S, and we're going to start using numbers. So instead of LDFS, you're going to see here an LDF, and instead of the sequence of arguments, we're going to say that it has 1 argument. That's all we care about, right? So what's happening here, right? We have a function application to the argument 2. The arguments, this expression, as you remember, is evaluated in reverse order. In reverse order, right? So we're going from here. This is first, this is second, right? So you're seeing the constant being loaded into stack first, and then we're defining a function all right, with 1 argument starting at location 4. Right? And now we're going to play a dirty trick, because I said, well, now we should have a go-to, right? And then we should skip the body of the function. But what a compiler will do is not place the code of the function in the middle of the main program. We'll actually put the code at the end and essentially just keep moving, right? So this is a simple optimization. Previously, what you would have seen would have been this going in here, and then you would have a go-to here, right? So call go-to the code of the function, and then it would be done, right? We don't have that anymore. The important thing to notice is that instead of LDFS, from this point on, our instruction is called LDF, and it's not using a sequence of arguments, it's just using the number of arguments, right? Because we're going to take advantage of that and map every symbol with a specific location in the environment. And this is what you can see here, right? So we're taking this variable x and saying x is going to be at location 0 in the environment, right? We're not saying LDS anymore. we're saying LD, and X is equated with index 0. All right? And we're loading constant 1, we're performing the plus, and we have a return. So whenever we perform the call 1 here, the environment that is being saved will have one location, right, with address 0, and then this constant 2 is going to be placed here, and whenever we're performing this operation, right, we're going to pull from location 0 in the environment and push on the stack. All right? And we have just added this X here for just to remind you that this is X, because normally it's not going to be there. What you're going to see is LD0, right? Which LD0 is going to take from the 0th location in the environment and push on the stack. Okay? So X has been silently replaced by 0. Not silently, right? Because X it's the only argument. Every occurrence of X is going to be considered location 0 in the environment. If you're going to have X and Y, we're going to put X at 0 and Y at 1, or vice versa, maybe Y at 0 and X at 1. They have to be different locations, right? And every occurrence of X is going to be equated with index 0. Every occurrence of Y will be equated with index 1, and then that's how the whole code is going to do, right? So whenever you would have had an operation on X, you're going to say LD0 to push the X in the stack to allow it to be operated on. And whenever you're going to see Y, you're going to say LD1 to take 1 from the environment, location 1 from the environment, and push it on the stack to allow it to be operated on. Okay? So, yeah, maybe I've been jumping the gun in one go. A lot of stuff gets introduced, but this is how things get optimized. Does this make sense? Okay, so as a side optimization, you are seeing that a procedure is being moved after done. So that's just. So this is a discussion that we actually had, and it's trying to explain why do we need to bind non-local variables inside the closure. All right, and we have already seen the explanation. Okay? So if we don't do that, then X will escape, and it may be bound by an even outer scope, which is not what we intend. All right? What is the disadvantage? It's not a real disadvantage. It's more of a different style of programming that the world has moved on from currently, right? So what you would be getting if you didn't do that was dynamic scoping. What we like to use is static scoping. All right. Any partial application can be converted into full application. All right. It's just a simple transformation. So let's see what's happening here. We have a function that takes an X, returning a function that takes a Y, which performs addition, and then F gets applied to 4. All right, so why is this a partial application? Oh, okay, because what happens here is that it's not clear from the outset that the result is going to be a function. So the result of this is a function, right? Which is actually shown by this type, right? What you want to do is make it very clear that it's a function. So return a lambda, right? And because this f, looking at its type, it takes 2 arguments, right? So whenever you see f, you want to see 2 arguments. You want to see it applied to 2 arguments, right? So in this way, every function application, by just performing this wrapping, every function application becomes a full application. All the arguments are consumed. And all right, so so this is the compiled code for the previous example. All right, having done that transformation, this is the code. Again, we are we are moving the procedures at the end, so we're not going to see the go-tos. All right. So, what are we doing here? We're essentially defining 2 functions, right? So we will be defining f, right? F is just a symbol, right? So starting here and ending here. And in the process of defining that, we're going to define another function that starts here and ends here, okay? And then finally, the whole thing is going to be a function that goes from here to here, okay? So essentially, we're going to start with this one, obviously, right? So we're going to have a function that has 1 argument, right, and is defined at line 11, which is very strange because there's no line 11. So it's probably 10. All right, so I'm assuming this is 10 or 13. I think this is 10. All right, so we're defining a function that has 1 argument is defined at line 10. All right, and so this would be the first thing to go into the stack, right? We're defining another function that has 1 argument and is defined at line 4, and then we're calling 1. Right, and then we're done. So this is precisely this function right here. Is that so? Let's see if we can see both at the same time. All right. So the function at so it doesn't look at all as the transforms to. Sorry. It looks like the one that is at the top, right? So let's make sure we identify correctly. So at 6, what I see at 6 is this, the last function right here. So that's at 6. Then this is the result here. And then I have the function at 11 and the function at 4. The function at 11, which is probably the function at 10. Takes a function with x from the environment and one argument. Alright, I'll have to get back on, I think this example is wrong, sorry for that. I don't think it's the correct main program. Because the main program is a function, is a call with 2 arguments, right? And the only call with 2 arguments is at line 6. Oh. So how many calls do we have? So we have one call here. We have only one call. Why do I have 2 calls? I'm not sure what this call is for. Call 1 here. All right, let's leave. I'll get back. I'll get back to you on this one. All right. So, recapping what we have in the stack frame, this was probably quite clear. And the next thing we move into is recursive functions, right? And recursive functions are not that different, all right, than regular functions. What's the only difference? Why would I have a problem in compiling recursive functions? If you think of the body of the recursive function, what symbol appears inside? Louder.
The function itself.
The function itself, right? So how do we solve that problem? Yes. All right. So I'm going to augment the environment with the function symbol, right, which has to be a closure. And what closure do I use? The one that is about to be created, right? So in LDFS, I will be creating a closure, right? In the LDFRS, I'm going to be creating a closure where the environment is going to have, so let's say the function is called f, right? The environment is going to have a symbol f whose value is going to be the closure that I'm about to create. Now I'm going to say, how is that going to be possible? Because I haven't created the closure yet, and yet I'm putting it in the symbol. Well, as it happens with memory, right? You know the address where we're going to put the closure, right? All the data structure is going to start at a certain address, right? So all I have to do is put the f in the environment has to point to the place where you're about to place the closure, and that solves the problem, right? So this creates a circular data structure, and that's fine because, you know, I mean, it's possible with recursion to go into an infinite loop if the code is not properly guarded, right? It's possible. So you're creating a potential for an infinite loop, but that's understood that it should be possible. So let's look at the definition of the recursive function, right? And we're going to add the symbol f for the time being as simply an extra symbol. So we're not putting it inside the v1 VM, right? We're just putting it as a standalone symbol as an argument to the instruction. Okay, and let's see what happens when we execute it. So when we execute it, the result of this instruction is a closure. It's a triple of, yes? Question? Okay. It's a triple, right? It's a triple of the return address, arguments, and environment, right? So what we do in this environment, we are placing a reference. F becomes maps into a reference to this closure C, where C is exactly this thing, right? So we're using this, we're abusing the notation a little bit. Sorry for my inability to draw straight lines. So we're calling this bracket C. We're abusing the notation. We're saying that this this operand, right, should be also known as C, and then what we're putting inside here is C. And this is possible because in memory everything is references, so we're just putting a reference to that and not the actual thing. So this should be clear. So at this point, what is going to happen? When I have a call, I'm just going to go and jump back to this PC+2, right? I'm going to, whenever I have F is a closure. The start of the closure is this PC+2. I'm just going to go back to the beginning of the function, right? But this is a call. So as I go back to the beginning of the function, I'm also going to save something in the runtime stack, which will allow me to return from the recursion and restore stuff and come in these nested returns and eventually get out of the function whenever the execution is completed. Right? So this is all we have to do. It's not a big deal. Is this clear? It's a little trick, but if you're experienced coders, this should not be difficult to implement for you, right? You've seen recursive data structures before, so it should be straightforward. And there I was about to press escape again. Clear? Yep. Very good. So we're using the same call. Now, let's think of the mechanism, right? So you're going to execute Fibonacci, right? So x is greater than, or factorial, recursive factorial, even simple. So n is greater than 0. So you're going to start computing n times factorial applied to n minus 1, right? So you're going to take n, put it on the stack, right? You're going to see that I'm applying f to n minus 1. It's an application. You have to go in reverse order. You compute n minus 1. Actually, yeah, you compute n minus 1. So you're going to put n on the stack, 1 on the stack. You're going to do a minus. You're going to extract n and 1. You're going to put back the result of the subtraction, right? Then you're going to see f. You're going from n minus 1 in reverse order. And f is the recursive call. So we're going to take the same triple, and you're going to put it on the stack, and then there comes the call instruction, right? Call 1. So at that point, you take the triple and you jump to the beginning of what? The same function, right? As you jump, it's a call instruction. The runtime stack has to get a new record, which has the place of computing f applied to n minus 1, right? Because you have to go back there and you have to multiply by n and actually exit, right? You have to continue that computation. But now you're starting again from the function, right? You have another n. It's the, so let's say the initial argument was 5, right? So now your argument is 4, still greater than 0, right? So you have to go and compute 4 times f applied to 4 minus 1, right? So the same cycle, put n into the operand stack. So now you have 5 on the operand stack from the previous call. You have 4 from the current call, right? And you see f applied to 3. F applied to 4 minus 1, right? 4 minus 1 goes to the stack, minus, compute 3, f applied to 3. F goes is the same closure. Then you jump again, but you have created another runtime stack. So you have a runtime stack for n equals 5. You have another runtime stack, stack frame, for n equals 4. And you're going to keep putting stack frames there until you encounter n equals 0, and you can return the value 1, and you don't perform any further calls, right? There's no residual arguments in all this. So as you hit the first return, you're going to go back to the point where you're computing 1 times 2, right? And you're going to hit return and compute 2 times 3, 6. Then you're going to hit return 6 times 4, 24. Then you're going to hit return, compute, right? So what happens with the runtime stack in all this process? Keeps growing. And then as you hit the first return, shrinks a little bit. But after that, you hit the next return, shrinks a little bit. After that, you hit the next return and shrinks a little bit more, right? And you're coming back and popping all the stack frames from the stack, right? So if you have recursion, the natural tendency is to put a lot of, as you go deeper into the recursive calls, put a lot of records on the runtime stack and come back. This is the reason why in most languages, if the recursion is too deep, you get what? Louder. Stack exceeded, right? The typical exception is stack overflow, right? You get an error message, the program bombs with stack overflow. All right? So this is the type of recursive that we call cascaded recursion, right? So it's because we've written the program in this way, right? So there's a delayed operation. So we're saying n times factorial applied to n minus 1, right? So the times has to happen after the recursive call, right? I have to come back from the recursive call, and only then I can perform the times and then return. Is that clear? Now, there's another way of writing recursive programs, which is called tail recursive. Has everybody heard of tail recursive? Tail recursion, who hasn't? Everybody, luckily. Everybody, so then that's going to make my job very easy, right? So I'm going to use F because I don't like to type too much. And we could write factorial in this way, n and an accumulator. Right, so if n is equal to 0, if n is equal to 0, I keep forgetting, sorry. Man, not my good day. Return what? A, right? Else return right? So we're going to call this with, let's say, 5 and 1, and we're going to get factorial, right? What's important compared to the previous example is that this call to F happens as the last thing in that function, right? So the operation that previously was delayed, the star, is no longer delayed. First I multiply and then I call F. Okay? So think of how this will be translated into the code. I have the call to F and then come back and hit return. Does that make sense? So I'm going to call F with 5, with n equals 5, which calls F for n equals 4, which calls for F for n equals 3, right? 2, 1, 0, and then I return 120, and as I return 120, I return to the previous place. What instruction do I have there? Immediate return, right? So previously I would have had a start to do, a multiplication to do, right? In my previous version of the program. Now, you see, I call F and then come back, nothing to do. So I must be hitting this return, right? There's nothing. There's nothing delayed, and then I return from that one, and I'm going to hit return again. So I'm going to hit return, return, return in a chain, right? So theoretically, at least with what we have right now, we don't have a way to reduce the stack usage, the runtime stack usage. We're still hitting the returns, and we're still going to pop stack frames from the stack, and we're going to still use memory if the recursion goes too deep, right? We're still going to run out of stack if the recursion goes too deep. But the thing is, yes, you want to say something? Yes, so we're going to see how that happens, right? So we have to invent a virtual machine optimization. It doesn't happen naturally, right? So we have to detect it, and we have to use a special instruction for that. We have to detect the opportunity for tail recursion, and we have to employ a special instruction. Okay, so that's the point that I'm trying to make here. So even though between the call and return there's nothing to do, right? We are still performing all the calls, putting everything on the stack, and then performing all the sequence of returns, return, 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 and removing from the stack, right? And if we run out of stack, we're as stuck as we were before, right? Now, think of the following aspect. We have a call, and we know before we're making the call, we know that the return is the next thing to do after the call. What's the use of the stack frame at that point? Do I still need a stack frame there? Does it make sense? So the stack frame is useful so that when we come back from the call, the values that were there in the environment are restored. But since between the call and the return, there's absolutely nothing, there's nobody to take advantage of the restored environment. Okay? So I might as well reuse the stack frame. Instead of creating a new stack frame at the call time, I would say I would just reuse the previous one. Does it make sense? Because when I would return from the call, the immediate thing I'm going to do after that is return. Between call and return, there's nothing that would take advantage of the return of the restored environment. So I might as well destroy it before I go into the call. Right? So that's the tail call optimization.
Are you destroying or are you using?
Well, I can destroy and create, or I can reuse. What you're going to see is actually destroy and create, right? Because that's how math works. We can't effectively reuse. You're going to see that this first item in the stack is replaced by this other first item in the stack, right? And essentially this kind of sounds like I destroyed it, and then but what compilers will do is not deallocate the stack, not even manipulate the stack as well, simply go in and restore them. This optimization doesn't work just for recursion, right? Anytime I have a call that is followed by a return immediately, I can perform this optimization, right? But the problem here is that as I go into calling a different function, not the same function, the size of the stack frame is not going to be the same, right? So it's probably better to look at it as destroying and then recreating, because as I go into a new function, into calling a new function, I'm going to have to create a stack frame of a different size. Okay? But if it's exactly the same function, then it's exactly the same size of a stack frame, right? The stack frame is dependent on the function. It's the same size at every call. So we're going to introduce a new instruction which is called a tail call. Okay? Code that I have already shown you. Okay? And instead of using call, we're going to use tail call. Now, if we destroy or reuse the stack frame, so you can think of it as destroy and recreate, but the recreation corresponds to the next instance of the call, right? Am I still able to do a return? Right? So at all times I have only one stack frame. How many returns can I do? A number of returns equal to number of stack frames, right? So I can only do one return. All right? So the tail call doesn't need to have the return anymore. Why? Because, so I'm going to go from instance to instance to instance to instance to instance. The deepest return, where is it going to go? Yes. So no, the deepest return is going to go where? Okay, let's do a drawing. And I'm just going to, right? So there are instances. right? But they're the same code. So from here I go here, and this goes here, and this is the base case, and hits return. Now, where I was at this point, normally I would have a return here, right? And I would have a return here right after. The base case has a return at the bottom. Do I get to execute this return at all? When I execute this return, where do I go back? And there's a main program. Obviously, there's a main program. And this program from somewhere calls this function. Right? So at this point, I have created a stack frame. And at this point, I would normally create a stack frame, but I'm reusing the previous one. I'm reusing the previous one. I'm reusing the previous one. When I hit this return, where am I going to go? So, louder. Yes. From here, I'm going to go straight to here, right? Right? So, first of all, there's only one stack frame, so I can do only one return. But when I hit this guy here, the first stack frame created here, what return address is going to contain? This one, right? And when I'm going to reuse it, I'm going to change what? I'm going to change the environment, but I'm not going to change the return address, because I have no use in coming back here. I don't want to come here to just do a return, right? So I'm going to leave the return address the original one. So I'm going to go here, right? Again, I'm reusing, but I'm leaving the address, the return address as the original one. So I don't need to do this anymore, right? So there's the return here, that is the recursive return, and there's the base case return, right? This one is the base case. So this return will not execute because it's a base case, and then somehow the logic took me to the base case return, right? So this return will take me back straight to the main, which means that whenever I perform the optimization, if you look here, I don't just replace the call. I replace the call plus the return with the tail call, right? Does that make sense? Right? So this is the tail call optimization. So the tail call will reuse or destroy and recreate if you want. It's actually easier to think of destroy and recreate. But it will also replace or remove the return. The return doesn't need to be there, right? So the call followed by the return is replaced by this tail call, right? And that's it. This does not need to be applied just for recursive functions, but for any functions that are the tail call, the last call in the body of the function. Okay? So I would like to look at the semantics. All right? So let's see what happens here. When we perform the call, as usual, right, it's just a call. So what we have at the top of the stack is a closure. We have some arguments, we have a PC, we have an environment, and we have a stack frame. So whenever we perform the tail call, we're piggybacking on an existing stack frame. The stack frame must exist. All right? Why is that? Because I want to reuse this thing. I want to preserve the original return address. Clear? So there must be at least one stack frame there. So what are we going to do next? What's the next state? Obviously, we're performing the call. So we remove everything from the operand stack, right? We're jumping to the address given by this guy, right? We're performing all the usual things, right? We're augmenting the environment. So this environment from here is augmented with actual values from the operand stack. The interesting thing that happens is what happens with the stack, right? So you see this old record. We don't add a new record. We're essentially replacing this record by a different one, right? So that the length of the runtime stack remains the same. So the original return address remains the same. Even though we're going into a new function, we're going to return to the top level directly, right? We're preserving the original environment, right? So whatever environment was available here, that's the environment we have to use. These two things are actually coupled, right? I can't change one. I can't not change one, but change the other. If one stays the same, the other has to stay the same as well. And what happens here, right? I have some residual arguments, and I have applied S, all right? But so the call is for N, all right? The call is for N. But the function is capable of taking S arguments, right? So the essential aspect is here, right? I have S arguments, right? So what am I doing? I already have R residual arguments, right? I am consuming S, but I'm adding N, right? And N and S may not be the same. So whatever is here adds to the residual arguments. Whatever is here removes from the residual arguments, right? This is consuming. This is adding, right? This is saying I give you N arguments, and this guy is saying, oh, I can only consume S, right? So because this is essentially a call combined with a return, to a certain extent, right? We have to manipulate this number accordingly. Does it make sense? Okay. So the important thing is that the size of the stack has not increased. If you look at the call instruction, right, you will see that previously we would have our S, and after a call we would have our S prepended with something, right? Which means that the RS increases, right? So the call will increase the size of the stack, but the tail call doesn't increase the size of the stack. In that respect, it is memory constant. It is constant in the size of the memory that it uses. Okay, and that concludes the lecture. And hopefully you understand this part very well. Any questions?
You mentioned the tail call is not just applicable to recursive functions. It's
Yeah.
applicable to last.
To last call, right? So the tail call, right? So anytime you're going to have something like right, so define F, some arguments, right? So it's the definition is here. The last thing you're calling is G, right? You have return G, right? And somewhere else G is defined, right? And this might return an H of some arguments, right? So this is the last thing that happens in this function, right? So I would call G, and immediately upon returning from G, I would also return from F.
So this is another aspect of the tail recursive.
Yeah. So don't couple tail with recursive. So I mean, so tail recursion is an optimization technique for functional programs, right? Because traditionally functional programs did not have while loops. So the only way to perform iteration was via recursion, and then while loops as a means of recursion don't use constant memory. So people looked for whoever was working with functional languages and inventing them, essentially, created an equivalent means of performing repetitive computation with using constant memory at the same time, right? So this is the solution they have found. But the solution, and it was specifically targeted at recursive functions because that was the only way of performing repetitive computation. But it just applies to any kind of last call Right? But that was realized later. So initially, people said, "Oh, yes, we have a solution for recursion. Whenever the recursion can use constant time, we can detect that, and we can make it use constant memory, not constant time." But later they said, "Oh, wait, I don't just need to apply it to recursive. I can apply it to any last call." And then it was generalized. So now it is known as tail call optimization, not recursive tail call optimization. So it's just tail call. It is very useful, for instance, in mutual recursion, because sometimes the only way you can, or the most readable way of performing repetitive computation is F calls G, G calls F, right? It's very common when you perform tree traversals, complicated tree traversals, right? For readability, you create functions that work in tandem. They take different number of arguments, right? And you have the situation where F calls G, G calls F. If both F and G, the calls to F and G that are inside, they are tail calls, then again, you would be using constant space, which is essential here. Okay? So, by the way, any computation can be converted into tail recursive. Any recursion can be and can be done using iteration, using while loops, right? Even Towers of Hanoi, which is the most typical recursive problem, right? It's so typical. It is used as the epitome of recursion because it's very difficult to come up with an iterative solution there, right? But it's nevertheless possible. So we use Towers of Hanoi because we want to say, oh, look at recursion, what an important problem-solving method it is. There's this problem that you wouldn't be able to solve otherwise, and recursion provides a very simple solution to it, right? And that's how you learn recursion. So then the interesting thing is, how do you solve it without recursion? Is it possible? And of course, now not having recursion is still Turing complete, so there should be a way. The thing is that there is a standard technique. I can take recursive code and make it non-recursive by a standard transformation. Actually, the standard transformation is captured here. The virtual machine is tail recursive, right? This relationship here is tail recursive. Does that make sense to you? You see, not all the relations that we have defined would be, so all the relations that we have defined are sort of recursive, right? And when some of them are not tail recursive. This one is. This one you can implement it as an iteration, right? You have a loop, you have a big case on which instruction is current, and you have a data structure that encodes this, and you move from one data structure to the next. It's a while loop, right? So that should give you an idea on how you might be able to take an algorithm like Towers of Hanoi and implement it with a while loop. So try it for your own edification. It's a very useful exercise. Okay? Cool? Okay. You all look tired. I also feel quite tired. How are the labs going? Are you enjoying the hacking? Yes, some smile, some not so much. Okay, see you next time. Thanks for coming.